Okay, so now that we've configured our network components that apply to both wired and wireless architecture, we have wireless devices and protocols that have their own unique security challenges. So, when it comes to wireless networks are going to be fundamentally networks that do not solely rely on physical cabling and network's infrastructure. Instead, data in a wireless network is going to be transmitted through low frequency radio waves, and these signals are going to be in and these signals are going to be emitted with these waves that and these signals emitted on these waves can cover large or small distances and can pass through physical objects like walls in order to reach their destination. So the advantages of wireless networking are going to be portability, saving on cabling, uh, being able to get through physical spaces, and this is going to make wireless communication really powerful. However, because of wireless signals are just that in the air, it this is going to raise unique security concerns. Wireless antenna types. So, wireless networking signals can be amplified using different antennas. And two of the main categories of antennas are going to be omnidirectional and directional. And so directional antennas are going to transmit signals to a specific point. And as a result, they typically have a large amount of gain. And this gain is actually the reliable connection range and power that is of a signal that's going to be measured in decibels. So these are going to be less susceptible to interference than an omnidirectional antenna. And so, an omnidirectional antenna is going to send and receive radio waves from all directions, and it's usually going to be the main distribution source of a wireless signal. So, if you're in class at Montgomery College, usually you'll see them in the center of the room on the ceiling. So, these antennas are going to be common on all wireless routers or mobile wireless adapters, and these devices are going to require providing or receiving service in all possible directions. And because it sends wireless signals in all directions, it's going to limit their gain. And so, according to these antenna types, um, we have specific antennas within each antenna category. So a rubber duck is going to be a small omnidirectional antenna that's sealed inside of a rubber jacket. And this is typical of most omnidirectional antennas. And these rubber ducks are going to have little gain. However, because of their small size, they're good for things like walkie talkies and two-way radios. Um, and then we have ceiling domes. So ceiling domes are going to be omnidirectional antennas that are commonly used to cover rooms or inside of a building. So the rubber duck is a lot of times what you may have seen in your house when you have those several different antennas on top of a router, and those kind of go in all different directions. Then we have directionals. So we have Yagi, and a Yagi antenna is a directional antenna that's primarily used in radio. It's employed in long distances as well in networking, and this is going to extend the range of hotspots. Then we have a parabolic antenna, and this is going to be a very precise directional antenna. These are going to be often used in satellite dishes. They have a real good gain, and because they're so precise, it's kind of difficult to establish a connection with a parabolic antenna because they're very precise. Backfire. So backfire are going to be small directional antennas that look similar to a parabolic dish, but they have less gain. Backfire antennas are going to be used in wireless networks to efficiently target a specific area without actually overextending that range. And then we have a cantenna. A cantenna is going to be a homemade directional antenna. It's specifically like a can, just like people had can radios or can telephones. So this can kind of extend the wireless networks, or they can help discover them. And so we could do this by placing a metal can over an existing antenna in an attempt to kind of increase its gain. 802.11 protocols. .11 protocols. So 802.11 is a family of protocols that are for wireless LAN communications between wireless devices or between wireless devices and a base station. So these are the common 802.11 protocols. First, we have 802.11a, which is which was actually created in about 1999, and 802.11a supports speeds up to 54 megabits in the 5 gigahertz frequency band. However, it only has a limited speed of about however, that speed itself has a limited range of about 60 feet, and depending on how we arrange our access points, it could be really limit our mobility. And then we have 802.11b. This was the first specification to be called Wi-Fi. It's also the least expensive wireless network protocol. 802.11b is going to have an 11 megabit per second transfer rate in the 2.4 gigahertz range. And 802.11b also has a range of up to 1,000 feet in an open area and about 200 to 400 feet in an enclosed area. So it is backwards compatible with 802.11. However, it's not interoperable with 802.11a. 802.11g, this is a specification for a wireless data throughput at the rate of 54 megabits at the 2.4 gigahertz range, and it's also compatible with 802.11b, and it operates at higher speeds a lot of the time. Then we have more current networks. This is, you likely have in your machines right now, an 802.11n or 802.11ac. 802.11n is a specification that has a throughput up to 600 megabits per second, and it's in the 2.4 or 5 gigahertz range. One important part about 2.4 gigahertz, which a lot of our stuff has gone through, is the fact that 2.4 gigahertz, a lot of devices run at that range, and so sometimes we have interference. Moving forward, when it comes to 802.11ac, this is basically one of the newest standards. It is the newest. However, we might be seeing 802.11ax out there now. I haven't seen a device that has it yet, but that's going to be the newest one coming up in the future. But 802.11ac has 5 gigahertz channels, and it is going to increase our throughput up to 1,300 megabits per second. So that is going to support your gigabit internet. Wireless cryptographic protocols. So we have WEP. WEP is going to use a 64-bit, 128-bit, 256-bit encryption using RC4. However, this was deprecated because it's basically considered a security hazard because it relied on an initialization vector to randomize its keys, and it had only a 24-bit initialization vector, and this was really vulnerable to attacks in order to predict the IV value. Then we have WPA, so that's Wi-Fi Protected Access. This introduced this was a security protocol that was supposed to fix all the vulnerabilities in WEP. It has improved data encryption through TKIP, which is stretches keys, and this was designed to replace WEP. It combines WEP encryption Then we have WPA. So this is Wi-Fi Protected Access. This was a security call introduced to address the shortcomings in WEP. And so it provides for dynamic reassignment of keys to prevent these key attack vulnerabilities of WEP. And then it also improved data encryption because it introduced temporal key integrity protocol, TKIP, which is a security protocol that they made to replace WEP, but it's also a key stretcher. And so when you combine existing WEP encryption, it's going to provide a 128-bit key that fixes that short key length issue that WEP had. And however, this is kind of still vulnerable to attacks in which small packets can be decrypted. And so now we have WPA2, and this is going to improve on WPA by implementing all the components of 802.11i. And so WPA2 is going to include advanced encryption standard ciphers, along with counter mode with cipher block chaining message authentication code protocol, which is CCMP, and that is an encryption for greater security to replace TKIP, which was in WPA. And this provides for a 128-bit encryption key. We also have EAP, so this is Extensible Authentication Protocol. This is a framework that enables clients and servers to authenticate with each other using a variety of different plugins. And because EAP does not specify which authentication methods should be used, it enables a choice of different authentication methods. So there are several of them. There is EAP Transport Layer Security, so that's going to require a client certificate for authentication using SSL TLS. Then there's EAP Tunneled Transport Layer Security, EAP TTLS, which is going to enable a client and a server to establish a secure connection without mandating a client-side certificate. Then we have Lightweight Extensible Authentication Protocol, which is LEAP, and that is going to be a Cisco proprietary EAP implementation. And then we have EAP Flexible Authentication via Secure Tunneling. So that is EAP Fast, and this is meant to be a replacement of LEAP that's going to address any shortcomings in LEAP. We have IEEE 802.1x, and this is a standard for encapsulating EAP communications over a LAN. So 802.1x was later adapted to work with wireless LAN technologies, but 802.1x provides for port-based authentication. So 802.1x with a capital X is not to be confused with 802.1x with a lowercase x, which is a family of wireless networking protocols. Then we have Protected Extensible Authentication Protocol, and that's PEEP, right? And so this is an open standard developed by Cisco Systems, Microsoft, and RSA. And like 802.1 capital X, PEEP is not technically a EAP method. However, it's a way of encapsulating EAP communications using a SSL TLS tunnel. And so this is going to make PEEP function similarly to EAP TLS or TTLS however, EAP TTLS is going to support more authentication protocols than PEEP. And then we have Radius Federation. So Radius Federation is going to be a network authentication protocol, and federation is going to imply a shared level of trust between different networks, and this is going to be an 802.1 capital X standard that is often used with Radius in order to carry out port-based authentications. When it comes to VPNs and open wireless networks are a major security concern when addressed directly. And so because they're insecure, attackers can perform any number of attacks on that open network, and they can also compromise each individual user's communications. So when we're forced to use open wireless connections, we should tunnel through using a VPN if we can. So VPNs are going to provide authentication mechanisms to encrypt our data and transit over the internet. So even when we're using an insecure wireless hotspot, we're going to be secure. So one issue, however, is going to be that VPNs will not provide an adequate level of defense if they are not using secure tunneling protocols. So, for example, PPTP is vulnerable to man-in-the-middle attacks. So instead, we should use more secure IPsec protocols when tunneling through VPNs. Wireless client authentication methods. So when we configure a WP or WPA2 wireless network, we have the option of choosing between three methods of client authentication. So in WPA or WPA2 personal, this is going to be called WPA2 PSK. This is going to mean pre-shared key. And so this is a generated passphrase, something we could have made up or something like that. So so basically what it is the password that you have at home, right? You get this passphrase, and anybody that puts in your Wi-Fi password, it works for them, right? Or it could be something you made up, or it could be the number on the back of your router. However, because it's the same for everybody, the attacker can glean the password and use it to authenticate. And then we have WPA2, WPA Enterprise, and this is going to require that the client authenticates with a Radius server, and before it's granted access to the Wi-Fi network. So this is going to mitigate against attacks or an attempt to brute force the password. And so WPA2 Enterprise is better for larger networks. So you have to authenticate with your company or whoever they are before you're giving access to the company's Wi-Fi at large, basically. And then we have Wi-Fi protected setup, and so that's WPS. This is simplifying the authentication process for Wi-Fi networks by enabling the client to enter a PIN associated with a particular access point, like the one in your house. Or you could just press the button on the access point so that we establish our connection. Unfortunately, the PIN method on WPS is vulnerable to brute forcing, so we should avoid this when we can. Wireless access point security. So here we have several different security methods. The first of all is going to be MAC filtering. So MAC filtering is going to allow us to filter MAC addresses on our access point, so we can either blacklist devices that have undesired MAC addresses or whitelist devices that we authorize to be on our network. So filtering in either way can prevent unauthorized devices from attaching to our wireless networks. It can be useful, but MAC addresses are easily spoofed, so we shouldn't really just rely on that security method. Then we have disabling the service set identifier broadcast, and so that is that's your Wi-Fi name that you see on your list of Wi-Fi networks. So the access point is going to broadcast the SSID to show a human user that a particular access point is in range, and this is the default behavior in most situations. So we can choose to disable that SSID broadcast so that users have to know that there is an SSID in order to connect to it. And so disabling the SSID broadcast can protect against a casual user snooping. However, we shouldn't rely on it because network scanners can easily reveal that there is a Wi-Fi network available. We also have signal configurations. So a signal configuration is going to be adjusting the strength of our wireless signals so that we can contain the range of our network. For example, we might have a signal that exists beyond our premises, and this is going to be susceptible to a war driving attack and give somebody access to our network. So if it's not in range, this is going to help us to mitigate the attack. And so band selection and bandwidth signals can also influence the wireless security tactics here, because most Wi-Fi frequency bands are either in 2.4 gigahertz or 5 gigahertz, and so 5 gigahertz frequencies are going to offer greater bandwidth, and the 2.4 gigahertz frequency is going to offer a larger range, and this larger range can easily penetrate solid objects like walls, whereas though the 5 gigahertz can't, and it has a smaller range. And then we have deciding between fat and thin APs. So an access point is considered thin if it offloads certain tasks to another device. So fat access points are going to take on most of these tasks themselves. For example, a thin access point may offload authentication and generation of encryption keys to a centralized server. and this is going to leave the access point to just manage the connections. And then these thin APs are often useful in the 802.1 capital X authentication architectures, because these APs are going to rely on a centralized radius server to provide authentication services. And then these thin APs are also going to be managed by a wireless LAN controller. And this is going to be a device that configures the access point and offers switching functionalities. And then although controller wireless LAN access points may help us manage this network architecture, a FAT AP can help reduce complexity, because FAT APs can be configured by themselves without having another device. You could simply log in through the command line on a FAT AP and make all your settings there, rather than rely on a centralized service to do it like you have to do in a thin access point. So captive portals. Captive portals are going to be a technique that require a client to connect to a wireless network by authenticating through a web page. And so your packets are going to be intercepted until you complete the portal steps. And this is going to be used pretty much in public Wi-Fi spots in order to get a user to agree to the acceptable use policy. So, for example, this is McDonald's. When you go to McDonald's and you want to use their internet, you got to accept whatever they say. And then you're able to do what you want to, get on the internet or whatever. And then when it comes to authenticating, this is going to be like Comcast or Verizon, where if you're not at home, they make you sign in, and then you can use that wireless access point. Site surveys. So a site survey, in a general sense, is going to be a collection of information on a location. That includes access routes, potential obstacles, the best positioning of materials and stuff like that, for the purpose of constructing our network in the best possible way, our wireless network. So wireless networks go through a site survey phase in order to decide how exactly to design the network with respect to the hardware's location. And so a successful site survey is going to lead to networks and their users having a high quality coverage and bandwidth. And it's also going to be conscious of the security protocols and requirements of that network. So this is generally going to be accomplished by modeling the proposed environment using specific tools that collect radio frequency signal data. So, for example, radio frequencies emitted by a wireless access point might be blocked by a wall in a building, and so they may travel further in open air without that wall. So you, as the security professional, might determine that positioning that access point where the wall limits your signal actually prevents other users from attempting to access that point. So in doing that, we're going to uphold our company's protocols that stipulate not to extend a wireless network beyond a specific range. So guidelines for securing wireless traffic. When securing wireless traffic, we're going to want to choose wireless antenna types that best suit our infrastructure needs. We're going to want to choose a 802.1 lowercase x protocol that adequately meets our bandwidth and signal requirements, right? So 802.11a, b, c, etc., right? Then we want to configure our wireless networks with WPA2 encryption, because that's the strongest encryption right now. Consider using different wireless authentication protocols and how they're going to provide security in our wireless networks. We're going to want to use a VPN with strong tunneling like IPsec if we're using insecure open wireless networks. We're going to want to consider using WPA2 enterprises when we have a large corporate environment in order to take advantage of the 802.1 capital X radius authentication. Avoid using the PIN feature of WPS. Don't rely solely on MAC filtering and disabling SSID broadcast, because these MAC filtering can be spoofed, and SSID broadcasts, people can use tools to still figure out that you have a wireless network in range. We want to select the appropriate frequency band and configure the signal strength to meet our specific needs as an organization. We are going to want to consider using thin APs in a controller-based architecture to centralize our wireless operations. And then we're going to want to implement a captive portal requiring login credentials to protect against unauthorized users using our Wi-Fi hotspots. And we're going to want to conduct a site survey to determine the best possible ways to position our wireless infrastructure with respect to our security.